Thank you. And I told you guys, because of the whole scheduling snafu, that I would take the other homework assignment late, right?
Mhm.
Next Monday, okay. And next Monday, I will be gone.
And we
So-
won't be here.
So what I'm gonna do is, I'm about to hand out the second homework assignment that also says assignment 1, but it's not. Wait a second. Yeah, okay. And, wait a second. What was the one I handed out before?
The calibration spring one.
That wasn't homework.
HSI for woodpeckers.
HSI for woodpeckers.
Mhm.
Right. No, that's, oh, no, this is right. Yeah, this is right. Okay. No, this is wrong. There it is. Okay, yeah. That's what I want. All right. So this, yeah, I'm handing out the second homework assignment that also says homework assignment number 1, but it is assignment number 2. And I'm gonna say they're both gonna be due on November the 13th. That's the Monday after I get back, that I get back, okay? Good?
Okay.
So that gives everybody a little extra time, all right? So this homework assignment is on duck use days, or duck energy days, which they call it these days, okay? Does that ring a bell with you guys?
Yeah.
A little bit? Okay. So this is just kind of an exercise that makes this whole concept of duck energy days and how much corn you put out there on the land, and how much moist soil unit, and how much bottomland hardwood forest to support how many ducks. It makes it a little bit more real. It makes it pragmatic, okay? So I've given you, kind of like the other one, I've given you a scenario, and I've given you management goals with regard to how many ducks you're supposed to support. And I've given you some duck use day values for several different types of habitat. I've given you a few parameters. Some considerations are this. We have lost in West Tennessee 80% of our what habitat? Anybody remember?
Wetland.
Bottomland forest.
Bottomland forest specifically. We've lost about, overall, about half, a little over half, 55% of our wetlands. But in West Tennessee, you know, most of our wetlands were originally bottomland hardwood forest. And that's mostly, not entirely, but mostly where ducks were spending their time. Now, they were out on the open river floodplains and the open river channels as well. But those bottomland hardwood forests were extensive, and we've lost most of them. And you know, what they get from corn now, they were getting from acorns before, and a whole lot more as well. They were getting invertebrates from those bottomland hardwood forests, and the fats from the acorns and everything else. Not as much calories per acre, nowhere near as many calories per acre, but there was just a whole lot more acres. So what I want you to do as you do this plan is I would like for you to keep in mind the goal that we want to maintain this as much, as close to native as we can get, right? And we want to minimize our costs, of course. So, you know, you could plant the whole thing into corn and fail the assignment. You could say we're gonna leave the whole thing in bottomland hardwood forest and fail the assignment. You know, how much crop do we need? How much moist soil unit do we need? And of course, unmanaged moist soil unit or managed moist soil unit are closer to natural. They have a lot of natural vegetation. So we definitely want as much hardwood forest as we can get, but you know, better moist soil units than corn or rice or whatever. And diversity is good too, right? Better to have, you know, 2 or 3 different things than just all one different thing. So I hope that is enough to help you thrive in this assignment. Any questions for me about it?
None.
Right now.
Okay. When we get back.
Okay.
November
Both of
13th.
them, right?
The 11, 13, yeah, both of them, on 11, 13, yeah. Good? Cool, okay. Lab, okay, remember, no class next week, And lab, day after tomorrow, is gonna be sampling, vegetation sampling on the college farm. Has anybody had an internship where you were doing veg sampling, where you're sampling vegetation? It's common work for wildlife habitat research. A lot of internships where you're helping graduate students, you're sampling vegetation, looking at characteristics, physical characteristics of habitat. So what I'm going to give you today is about something like 9 slides, and I think they're on campus. Are they on campus? I think they're on campus. Of considerations when it comes to sampling vegetation. Okay, and we'll be using some of these techniques. So for starters, know that I'm going to give you here 4 methods for quantifying plant distributions and 4 methods for sampling plant distributions. And you should expect those 2 questions on the exam. And don't get them mixed up. Okay? Good? So this is methods for quantifying, for putting to numbers plant distribution. And if you think about it, it's kind of makes sense. How much does it weigh? How much does it cover the ground, like percentage? What percentage of the ground does it cover? I've broken that up into 2, haven't I? How dense is it? Just how thick is it? How dense? And how many of something are there? Are the 4 things? Okay. So I'm going to take each one of these in turn. Biomass, the weight of individuals, or the weight of plants, or the weight of species per unit area, can be measured in a variety of ways. But if we're looking at, for example, early successional habitat, you take a hay baler and bale it and just weigh the bales, there's a lot of ways that you can do that. That's not usually one of the most common ways, the common things that we're looking at. It could be if you're looking at a poundage of forage for cervids or grazing animals, but usually that's not what we're so interested in. Coverage, we look at a fair bit more. Proportion of the ground covered by plants or by trees or by a particular species, usually is viewed from above, like looking down, like at an aerial photograph, or looking down at a plot of how much grass or forb coverage there is, or something like that. But sometimes that's hard to do, and we can just as effectively doing it by looking up from below. How much canopy coverage is there, right? And sometimes we're interested in how much coverage is there from the perspective of a potential predator. So, as hiding cover or escape cover, so lateral coverage. So some examples of this could be here. This is, who can tell me what this is, this device? Anybody know? Yeah, this is called a spherical crown densiometer. A densiometer, or actually a concave spherical crown densiometer. And what it's used is to measure how much canopy coverage there is. You see you might be able to tell there's a grid of squares on there, okay? And the instructions are on the box, and you're gonna be using this in lab on Wednesday. We're losing a lot of our leaves, so usually you do this in the summer in a deciduous forest, but there'll still be some leaves under the oaks and the hardwoods. You randomly choose your spot, and you stand in one place, and it tells you hold it, a foot from your chest, and there's a little level to be sure it's level, and look in the mirror. And each one of those squares, you imagine there's 4 equally spaced dots in the square, and you count how many of those dots are covered by leaves, have leaves behind them in the background, leaves or sticks or limbs or twigs or branches. And then you do that for all of them, and then you multiply times 1.04, and it tells you your canopy coverage, okay, 90% or 80%. And you do that, so many places per acre, and take an average, and it tells you, okay, this stand has on average 76% canopy cover, or whatever, okay? All right. This is called a roll bell pole. And it's often used as a measure of lateral density to create an index of how dense it would be to cover, say, for example, for a turkey nest. How well would it be able to be hidden from a coyote or something like So what you typically do is randomly choose where to put it, and that string is a certain distance long. It might be 5 meters, it might be 10 meters. And you stand, you kneel so that your eyes are at a certain height, typically about a meter. And you count how many of those colored sections from the top down you can see that don't have any vegetation obstructing any of it. So, here they're all completely open, but if there was a blade of grass or, a couple leaves covering that, part of that, then you would count 1, 2, 3, 4, 5, that those bottom 2 were covered up. So you could say 5. And you would do it from the north, the south, the east, the west, take the average of those and say, okay, for this spot, our index value is 4.8. And you do that, several random spots throughout the field, take the average and say, okay, this field, our cover index is on average 4.8 versus this other field and this other species or this other seed mixture, the coverage is 3.2. Right? And the numbers in and of themselves don't really mean anything, but for comparing this year versus last year, after there was a controlled burn, or this fescue field versus this switchgrass field, or whatever, right? Who has used a prism before? Good, okay, some of you, all right. So a wedge prism is used in forestry to determine stand basal area, okay? You can purchase a metric prism or an English prism. Usually we use English prisms, which measures by the acre. A metric prism measures by the hectare, okay? And most prisms are 10-factor prisms, which means whatever value you get, you just add a 0 to the end of it to come up with basal area. So the way that it works is you randomly choose a place in the stand, and you hold the prism out at a predetermined distance, and you look at tree trunks through it, okay? And you spin, and you look at every tree trunk through it, and you go around and you count how many trees are in. What does in mean? Okay, when you look at the section of the trunk through the prism, and that section of the trunk touches the section of the trunk above and below the view through the prism, that's considered in. When the section of the tree trunk viewed through the prism is completely disconnected from the section of the trunk above and below it, that's not in, it's out. So we don't count that. So what it's looking at, it's a function of how close the tree is and the diameter of the tree. So if it's a big tree, it could be pretty far away and still be in. If it's a small tree, it can be pretty close for it to be in. So if you spin around and you count 6 trees that are in, okay, then at that spot, your stand basal area is 60 trees, or 60 square feet per acre, okay, for an English unit. If it were metric, it would be per hectare, okay? Make sense? Okay. And you do that in several places and take the average to get the average stand basal area. Good? What's the difference between density and basal area?
Number of trees versus square foot of trees.
Square foot of timber, lump of wood. That's right, exactly. Okay. Okay, next, density, number of individuals per unit area. So maybe we're counting snags, maybe we're counting logs, maybe we're counting rocks bigger than this big, or maybe we're counting white oak trees, or whatever it is that we're counting, just density, per however unit area. And then frequency, number of samples in which the species occurs. So maybe I put out 100 plots and I count at least one Christmas fern in 62 of those plots, so 62% frequency. That was a sample. There are 3 primary discrete methods of sampling: plant distributions, and then one that's remote sampling. So the primary discrete ones are plots, transects, and point quarter sampling. Okay, I'm going to talk about each of those in turn. It's pretty simple, pretty straightforward. Having said that, a lot of people miss a lot of questions about this on the exam. It's not hard, so ask me questions if you don't understand it. It's straightforward, okay? A plot is just something that has a defined area, okay? And if it's a small plot, we often have a little frame made out of PVC or something like that that we'll just put down, okay? If it's a bigger plot, like for trees, then or for shrubs, what we'll often do is we'll put a stake in the ground and we'll just have a string or rope tied to the stake that's maybe say 10 meters long, and we take it out to the boundary. We make it a circular plot. And I forget, you can figure out the length of the string you need using geometry to have a circular plot that covers 1/10 of an acre, for example. I forget how long, it's 17 feet or something like that. And you just pull it out and say, okay, here's your boundary. And you just maybe, you can put a paint mark, or you can't just move all the way around because there's trees in your way, right? So you have to go back in and then go back out over here and go back in and go back out to kind of define that circular plot. But there's a discrete size, okay? And you count whatever you're interested in within that plot, all of them. And sometimes you might measure them, how tall are they, or this many of this species and this many of that species, how much coverage within the plot. There's any number of things that you can do, and then you replicate it. You know, you randomly put several plots out to get a big sample size, to get a representation of that stand or whatever. You could put them on a grid, you could randomly place them, and they can be in different shapes. Commonly, historically, plots are square, and the term for a square plot is a quadrat. And there's a little confusion here. It's not hard. You just be sure you remember this, okay? Quadrat is a square plot. A quadrant with an N doesn't have anything to do with plots. It's one of the names for the third type of discrete sampling, which is point the spot where we do point quarter sampling, okay? This is not hard, but for some reason, a good bit of the class, usually over half the class, misses this question on the final. I think because it's a boring lecture, maybe, I don't know. But nobody's gonna miss this, right? Please.
Is the question, what is the difference?
A lot of the time.
Okay.
Yeah. I'm not trying to trick anybody here. It's really straightforward. I mean, this is a third grade thing, you know, this is not rocket science. Yeah, okay. Plots can be rectangular, plots can be circular. I read once that somehow, I don't know exactly how this works, somebody figured out that a rectangular plot that's got a 2-to-1 ratio on the width times the length, does a better job of capturing the variability within the plot than a square plot. So a lot of the times people make plots rectangular, okay? That's where, a lot of people make them square. Okay, so how big should a plot be? Well, it depends on what you're sampling. It's a little bit arbitrary, but we often stick to conventional sizes so that we can compare our results to the results of other studies, right? If every other study in the world has a meter square, and you're like, well, that's a little bit arbitrary, and really 2 meter squares makes more sense, or 1 3/4 meter squares makes more sense, and you do that, great, you might have something that slightly more effectively captures the variability within the stand, but it's not very easy to compare it to all the other studies out there, so it might not be worth it. So, for ground level vegetation, grasses and forbs, typically a meter square plot is common. And for what it's worth, we usually call a meter square plot a Daubenmeier frame, because that was developed by a dude named Daubenmeier, I think back in the 40s, a long time ago, okay? That's a square. Have any of you guys ever used a Daubenmeyer frame or a meter square plot or anything like that? They can be made out of whatever, often PVC pipe because it's super light. Did any of you guys go on the mussel sampling trip a couple weeks ago? We did plot sampling for mussels, and of course those plots were made out of rebar, and they were painted chartreuse because we were sinking them to the bottom of the creek and we needed to be able to see them. For bushes, shrubs, saplings up to about 3 meters tall, about 10 meter square plot. There's the radius, and that would be the dimensions if you made it a 2-to-1 ratio. For forests, usually 100 meter square plot, and then there's the dimensions. On the exam, I'm probably not going to ask you for these things, okay? But I will ask you for those basics. And usually about half the class misses that as well.
Do you always say this part?
I've been saying it for the past couple of years. I have. And they still miss it. What's up with that? Are you guys awake? Anybody need a sip of my coffee? Okay. You're good. You guys have got it. You're not going to miss it. Okay.
This one maybe.
How big is a plot for shrubs? Skylar?
10.
Yeah, 10 meters square. Yeah,
10
good.
square.
Okay, good. Okay, next is transecting, sampling. That's sampling along a line, okay? Sometimes plots are impractical, plants aren't distributed randomly, and this is where transects are especially useful if you're looking for differences along a gradient. Now, can you give me an example of a gradient that we might observe in nature, where plant species or distributions or density or something might change?
From a forest to a field.
That's not so much a gradient unless we've created a soft edge, a very gradual soft edge. Usually a gradient represents a gradual change, a graded change rather than an abrupt change. Okay.
About a forest that goes like up, like alpine, and it gets like all the trees start going and be like.
Did you increase out?
Okay, all right, so change in elevation. Could you go the other direction as well?
Oh, for sure.
When an upland forest moves down and you go from the 10-year floodplain down towards the 1-year floodplain, right? So you start getting from upland oaks down into bottomland oaks, for example. Yeah, so changes along a contour, good, in elevation. Can you think of another? It's related to, somewhat to contour. There's a word I've taught you that you always forget.
Karst.
Nope.
Aspect.
It is right there. So, what might we do here? Instead of going down the slope, what might we do? What is aspect? Don't you answer. What's aspect? What?
North and south side.
How would you define aspect? You've given me examples of aspect. Define it. I can define it in 4 words. I can define it in 3 words if I don't have to use a full sentence.
The direction the land is pointing, facing.
That the land is pointing.
Facing. The
Direction.
the sun is hitting.
Direction of slope. Right? Yeah? Good?
Yeah.
Okay. So if that's what aspect is, where do you put your transect? What do you do with your transect? You go straight up and down the slope if you're measuring aspect?
No.
No.
Other way.
You go along the slope where the aspect changes, right? Yeah. That's another example of a gradient. So these are, and there's lots of other ways and places you can do it as well. In a stream, perhaps in an estuary, where you go from freshwater to brackish to saltwater, a long transect, look at differences in that. Yeah. Now, most just a classic traditional transect is a line transect, but there are situations where you can create a transect and say, I'm going to measure anything within a certain distance of the line. I'm going to count any Christmas ferns within a meter of the line. Okay, and my transect line, is 100 meters long, but I'm saying anything within 1 meter of the line, that's a plot. It's just a really long ass plot, right? We call it a belt transect. It's kind of a hybrid between the two, sort of. Does that make sense? And a transect, depending on what you're doing, a transect could be, could be 10 feet long, or it could be 100 miles long if you're flying a transect counting waterfowl or something like that, right? So, a transect can be, any spatial scale at all. A lot of the time we use transects in grasslands. You put them randomly if you're just measuring some single habitat, so because you don't have to be measuring a gradient, but if it's along a gradient, you put it along the gradient. You don't just okay, we're on the slope, we're gonna put it any direction. No, you put it down the slope or along the slope to get access. A lot of the time for walking transects, looking at discrete vegetation, there's something like 10 or 25 or 50 or 100 meters long. We'll do a few of them. Sometimes if we're looking at frequency, we'll put tick marks on our line. Our rope will have a rope with a stake at either end of it. Sometimes you just reel out a 100-meter tape and you put tick marks every 10 meters and say, okay, within every 10-meter section, how many times does this tape cross over a log or a whatever it is that I'm interested in, this type of plane? 3 for 10 meters, none for 10 meters, 7 for 10 meters, none, this thing is every 10 meters and you get another count. We can measure intercept length along a transect to get density, indices of density or coverage, either of a species or by what we call perpendicular projection of foliage. So I've got this gives you an example. So you got your stake, you've got your line, and there's a couple ways you can do it. Okay, if let's say this is your species of interest, this one and this one, you can measure along this line this bunch grass, say, it takes up 5 centimeters here, and it takes up 8 centimeters here, and you just add together all those centimeters of bunch grass, basal rosettes. Or maybe you're interested in overhead coverage of the shrubs. So you measure from here to here, and from here to here, and you add up all those measures. Just depends on what your interest is, what you're studying, what you measure. Does that make sense? Okay. The third discrete measure is point quarter sampling, and that's also called quadrant sampling. That's right. This is a method that allows us to sample more efficiently if the density of what we're looking for is highly variable or very low. So imagine a situation where you're looking for ginseng, let's say, and you put down a plot, no ginseng. You put down another plot, no ginseng. You put down 1,000 plots, no damn ginseng. I know there's ginseng in the woods here, right? But my plots just aren't hitting it. It's taking me forever. So what this involves is randomly locating a point, okay, and then dividing all of the land around that point into 4 quarters based on the compass. North from that point, use your compass. North is that way, south is that way. So you imagine an imaginary line through your point that goes north and south, and another one that goes east and west, okay? So from that point, you've got one quadrant, right, at 1 quarter that goes from north to east. And what you do is you do a search until you find a ginseng plant and how far away it is, okay? And then from east to south, south to west, west to north, and in every one of those quarters, you search until you find a ginseng plant. And it could be a meter away, or it could be a mile away, but you do your search until you find it. And then you just add up, take the average of those distances. And then you do that in several places. So that allows you to more efficiently get to what you're looking for if your sample size is very low or variable. Does that make sense? Okay. So that's why it's also called point quarter sampling. Point, and then the land is divided into 4 quarters off of that point, or 4 quadrants. Good? Okay. I just said all that, didn't I? Good. Okay. Oh, there we go. Maybe you're wondering in each quarter, how far to a ginseng plant, or how far to the nearest log, or how far to the nearest snack, or how far to the nearest road, or to the nearest open water, or whatever, right? How far to whatever you're doing. And the fourth method is not discrete. It's anything that's indiscrete, that's looking at things from a distance using remote technologies such as aerial photographs or satellite projections, and Google Earth and all the apps out there in the world, like you've been helping us with the lab, have made that so much easier today to use these things. Like Damon said, he just uses that on his, on his phone in his pocket, and is able to do things that used to require his mainframe computers to do. What? Any guesses what that image is?
Weather patterns?
No. First of all, any guesses where it is? You're not gonna guess. That's Wyoming. Now, any guesses what the colors represent?
Elevation changes.
Mm-mm.
Where specific animal is that? Like
Closer.
distribution rate?
Vertebrate richness. That's a good guess. Yeah, vertebrate richness. How many species of vertebrates there are in different parts of the state. So, that could be the same thing could be done with plants, and there's actually lots of satellite imagery available that's done in like infrared and such that can tell you the difference between a conifer, where you have conifer versus deciduous forest and that sort of thing. So those tools have been used for decades, and it's easier and easier to use them today. So usually with GIS, with ArcInfo, and so this is for, of course, landscape scale stuff, not just stuff. Is that it? Oh, no, it's not it. Okay, that's right. There's a lot of indices available, all sorts, that give us some sort of a way to compare characteristics of habitat among places or in time. This is an example, an interspersion index. What's interspersion? This would be from Wildlife 250, which you haven't had, so.
Dispersion between something.
You can't use the word in its own definition.
It doesn't say dispersion, it's dispersion.
Huh?
Those are two different words.
Dispersion between.
Dispersion between. It's inters.
Can you use just jargon to come up with a definition when it comes to habitat? What is interspersion?
Between two different habitats.
Let me see if you remember this from Wildlife 250. Here's a farm, 1,000 acres, sorry. That's forest, that's field. Here's the next farm, 1,000 acres. Forest, field. What's interspersion?
It's like throughout. It's like broken up throughout.
How do you put that into words?
English is hard.
So the bottom one is more interspersed, right? You figure that out. The bottom one is more interspersed. So how do you put that into words? English is hard, but it's good critical thinking to practice this. I know that's not what this class is, but it's still good for you.
I guess more diversity in the different habitats.
They're equally diverse.
Same habitat split over a larger area.
That doesn't quite get to it. Let me see if I can work in that direction, and maybe y'all can improve on it. This bottom one is more interspersed because it has more patches that are smaller. And the top one is less interspersed because it has fewer larger patches. So if we use jargon, we could say the degree of patchiness. That's jargon.
It's patchier.
Right, okay, all right, good. So, this interspersion index takes a piece of property, and you have to use some sort of a rectangle, and you go from, or square, and you go from one corner to the next, and one corner to the next, and you count how many times the habitat changes, okay, how many edges these little two lines pass through. So here you've got 1, 2, 3, 4, 5, 6, maybe. There's one there, 7, 8, right? So 8 edges over 20 acres, your interspersion index is 0.4, okay? Here's my house, my property. There's an edge there, 1, 2, 3, 4, 5, 6, 7, 8, 9. I picked up 11 if you count the pond. 11 edges over 25 acres, a dispersion index of 0.44. The number in and of itself is meaningless. That's the nature of indices. They're only useful insofar as we compare two places at the same time, or one place at two or more different times. So my place beats my neighbor's place for interspersion.
Boo your neighbor.
That's
Boo.
right. Well, yeah, bless his ignorant heart. He doesn't know, or he doesn't care. Yeah, it's all good. But so this is an example of lots of tools we can use depending on what our goal is, what our interest is. Right? Good. Yeah, that is it. Okay. So short go today. You'll break into teams of, depending on how many of you are, maybe 2 teams. Well, there's usually 3 things to do, so I might try to break into 3 teams. We'll see how many of you there are. 3 teams of 2 would work, and it'll take probably a couple hours to get through the lab on Wednesday. So we'll meet here. We'll go to the van and drive over to the college farm today. All right.
Sounds good.
Good deal.